Okay, so we've come to friction, right? So this is one of the biggest applications of Newton's laws. Okay, now everything up until this point we've been focused on a frictionless surface, but we've ignored it, which means we didn't account for this kind of what is actually going to oppose motion. So what happens is friction will exist between two solid surfaces because even with the smoothest surface, it's quite rough if you go down on the microscopic scale, right? And there's going to be three types of friction, two that we're going to focus on, one that's not going to be so much right now. The one that's not going to be so much right now is this rolling friction, which is actually the lowest of the frictions. Okay. Sorry about that notification. Kinetic friction is when an object slides along a rough surface. So you look at kinetic, right? We talk about motion. And the main point is that, again, it's moving friction. And then we have static friction, which is the friction prior to the movement of an object. And so what happens is they actually use the same mathematical formula, just one uses an equal sign and one uses a less than or equal to sign. Okay, so again, here it just said that the equations are going to be very similar. And so the static friction is going to have this, sorry, I want to make sure we have a nice looking equation there. So the static friction will have a less than or equal to sign, because if you're less than that number, you're not going to be able to move. Okay, so what happens on the left side has to be greater than or equal to that friction on the right-hand side. And then the kinetic friction will now have our equal sign, right? So to keep it moving at constant velocity, you have to apply at minimum the kinetic friction. Now we have this weird looking symbol in there that is what we call mu. And what that is that is the coefficient of friction. And basically that number tells us how easy or hard it is for an object to move. And then off here to the right, in this, we have just some basic, just some examples. So like, for example, a wood block on wood floor, the coefficient of kinetic friction would be 0.2, where the static friction would be 0.4. Okay. And in general, what you'll see is that mu k will always be less than mu s. Okay. So it'll be you always have to apply more to get an object to begin to move than it is to keep it moving. Okay. If you think about those furniture sliders that you put under, okay, those will decrease the static friction so you can get them moving. But once that thing starts moving, it's pretty easy to move past that. Okay. So we're going to do a little bit more involved example here. So it's very similar to the last video where we were talking about the inclined plane or the modified Atwood machine. So what we're going to do is we're going to treat this as a whole system, but understanding that now we have friction down here, okay? And so what we're going to do is, first thing we're going to try to find, what is the range of values for this mass here, so that it doesn't go, so that it doesn't slide up the incline, right, or go down the incline, okay? So what does that mean? When we're going down the incline, our friction will go up, and when we're sliding, if we're going up the incline, our friction will go down, okay? And so we're going to have to do that twice. And so what is pulling my system? I have FB, right, or FG sub B, and then I have FG of A, in the x direction. Now, if I'm looking at for one end, let's say B is going to go down, which makes A going up the incline. And then that would make my friction this way. Okay. In fact, that would be a static friction. And then my other end will be, right, my friction will not actually be going up the incline. Okay. And so if I do, so I've got all this going in the x direction. So I've got FG AX plus FS minus FGB equals 0. And so what I'm solving for is in there. So something to note is that the friction even though it's mu times the normal force. But the normal force in this case will come from the y component of A, right? And so I'm going to have mg A sine theta minus or plus mu mg cosine theta minus mbg, and I'm going to solve this for mb, but notice I can get rid of g's because it's going to equal 0. And so all I have to do is add and subtract. So mb will be ma, and let's do a little algebra cleanup. So it'll be ma sine theta minus mu cosine theta. And so that would be give me one end. Okay. And so that'll be 10 times sine 37 minus 0.4 cosine 37. Let me grab my calculator. I didn't finish this calculation on my notes. So it's going to be 10 times sine 37 minus 0.4 times cosine 37. All right. And so the low end, so if I go 2.82 kilograms, it'll start to move. And then I know this slide's going to get messy. I'll do it in a different color. So then basically my equation will be the same. So mag sine theta, but the difference would be in this case, in my first case, it's a plus. This time it would be a minus. So it would be mu. I'm sorry for writing over everything. So it would be sine theta minus mu mag cosine theta minus mbg equals 0. Right? And so the same canceling, all the g's would go away. And so I end up with mb equals ma maybe sine theta. Oh, sorry, this should be a plus. So that one should be a minus. I apologize. Plus mu g cosine theta, right? And so it's going to be mb equals, and it's going to be 10 times sine 37 plus 0.4 times 9.8 times, oh, sorry, I canceled out the g's. I don't know why I kept that one in there. So this, let me just make it look nicer for you. So it'd be mu cosine theta, right? It says mu, sorry, making a lot of mistakes in this video. So it'd be 0.4 cosine 37, and that's going to equal 10 times sine 37 plus 0.4 cosine 37, and we're going to get a high end of 9.2 kilograms. So for it not to move, mass B has to be between 2.82 or 2.8 and 9.2 kilograms. So that would cause the system to stop. Okay. Now, let's figure out what would be the acceleration. Okay. If now it's moving in a kinetic friction of 0.30. Okay. So basically, we would have the same setup, right? But so it'd be mag sine theta plus mu mag cosine theta minus mb, right? So if I'm putting down the incline, right, is going to be my positive. And again, I mean, you could do all this as you want, right? In fact, I'm looking at my notes and I've got it all. So this would be plus and these two be minus. So I'm going to go with, it's going to go in the direction of the motion. So what I'm saying is this is positive, and these two here will go down the incline. So acceleration would be mbg minus mag sine theta minus mu mag sine theta, all that over total mass. So you plug in your numbers, and I'll save you a little time. but your answer will be 0.878 meters per second squared. I know that slide's like all over the place, but here's our answer to A. Here's our answer to B. Okay, so we have two more topics in this unit, which are going to be universal circular motion, and then we're going to talk about essentially the calculus of Newton's laws, which will be velocity dependent